Hello and welcome to this presentation of our CS-480 Capstone project, Loombreaker. I'm Joe Burchett. I'm presenting on behalf of my team members, Zach Heimgartner, Carrie Nickel, Marcus Pappas, and Keelan Pilchner. Our project has been advised by Dr. Nina Peterson and Professor Casey Blamiris. A lot of us have noticed that there are difficulties with modern web search, particularly with large search engines like Google. Search engines have optimization incentives where they want to deliver content that is most commonly requested by users or which will drive ad views. Because of this, it's difficult sometimes to find information about more niche topics or things that are outside of the mainstream. Additionally, we've seen a significant rise in the use of generative pre-trained AI, things like ChatGPT. One of the difficulties that we find with things like this is that we don't have any way to verify the accuracy of the information that the AI model gives us. So the goal with our project is to explore whether or not it's possible to use smaller scale search and AI tools to build topic-specific search tools that will allow us to do deep search on the web. So we're going to discuss that. I'll give you an outline of what we want to discuss. This introduction, I'll give you an overview of how this system works and the workflow of the interacting components. We're going to move through that fairly quickly because I want to focus a little bit more on an explanation of the AI components. This audience is a math club, so I'm expecting that we're going to have a little bit more interest in that space, so we'll devote some more time to it. I want to give you an example of how this application works, at least some screenshots, and I'll show you how this Discord bot we've built interacts with our Markov bot. And time allowing, I may show you some of the source code. And then we'll conclude this with some explanation of what we think we might be able to do with this system in the future. All right, so before we move on, I want to give a quick shout out to my research assistant who may or may not make an appearance during this video. He tends to get a little bit curious when I'm talking at the screen and there's nobody here, but we'll see. Again, we're pre-recording this, so this gives you the opportunity to ask me questions during the presentation. You can reach out to me at jpburchett@lcmel.lcse.edu. Hit me up on Discord with Troglodyte as my username. You can find me on GitHub. It's probably a little bit more appropriate to ping me there later. Or if you're in the Zoom chat here, pop in and ask a question. I should be able to answer it live. And technology permitting, I should be around after this video to answer any questions or discuss anything that's interesting to anybody. I can send you the slide deck, I could send you source code, whatever it is that you're interested in knowing about this project. Okay, so let's move on to an overview of our system. Generally, we have three categories of things that we have deployed to the open internet. First, we have some set of middleware, things that are third-party software that is produced by somebody else that we're using to support our project. We're running this third-party software along with our custom-developed software on top of some Azure infrastructure. In Azure, we're running an Ubuntu VM. We have things like firewalls, a DNS setup so that we can set up a public web presence. Our third-party middleware includes Nutch, which is a web crawler. We'll discuss what a web crawler is in a moment. Solar, which provides indexing and search utilities for web documents, web pages, basically. We'll explain that a little bit more as well. We're not going to talk a lot about CertBot or Nginx. CertBot provides SSL so that our website operates with HTTPS, and Nginx is a web server which proxies to applications that run behind it and provides an SSL interface for other things. I'm not going to talk about those much. Most of what we're going to discuss right now is our software, what we've developed. There are four things that we're interested in here, well, three really. We have an AI core, which provides a Bayesian network. It runs a Markov process, which cites sources from source material. There's a text pipeline that does some processing and ingestion of text. Loombot is a Discord bot that interfaces to, it provides an interface between Discord and our Markov software that runs in the back end, and Ionic, which provides a web interface to our AI core as well. We had intended to build a REST API using Python Flask. We didn't quite get there. So what we're presenting today is Ionic using static content in some mocks. It's real information that's been produced by our bot, but it's not being produced dynamically. However, our Discord bot does interact with the backend dynamically and produce dynamic content. So one of the things we hope to do in the future, if we continue to work on this, is actually develop a REST API so that we can present a homogeneous API to both the Ionic web app and to the Discord bot. Okay, so let's talk a little bit about how search engines work. There are generally four things that we're interested in doing when we're building a search engine, any size search engine, our little tiny one or something big like Google. We want to be able to crawl the web. We start with some set of seed URLs. These URLs are just websites that we're going to use to begin crawling. Our crawler is going to go out, it's look at those web pages, and it's going to find links to other web pages. And it'll use some algorithm to determine which websites it should continue to crawl down those links. We're using Apache Nutch to crawl the web. Next, we need a way to retrieve and index our documents. So we need to store them somewhere, and we need a way to retrieve them quickly. We're using Apache Seller for this. There is a convenient interface between Apache Nutch and Apache Seller so that Nutch can take those documents and put them in the index pretty easily. It also adds some metadata, and it makes it so that these documents are searchable. Next, a search engine needs a PageRank algorithm. So you have some number of documents, millions, billions, trillions. In our case, it's something like 30 or 40,000. But we have documents that are sitting in your index. You need a way to rank them when you do a search so that the things that are most relevant are at the top and are returned to the user most easily. We're just using the default for Apache Seller. It works well enough for our purposes. We're not super interested in investigating the PageRank algorithm in Seller right now. We're more interested in the AI components, so we just use the defaults. And finally, we need a way to present that index data to somebody. It's a search interface or something like that. Seller uses something called Lucene, which is it's a structured query language of a sort that allows you to retrieve documents from the index. So we write a fairly static Lucene search string that allows us to search our search engine and build our Bayesian network. So that's basically how all the search engines on the internet work, as far as I know. I don't know, maybe there's some special stuff out there that does something different. But we crawl the web, we index the documents that we find, we have some way to rank the documents so that relevant documents are returned most easily, and then we have some way to present a search interface to people. And this is what we've done with Nutch and Seller. Okay, so given these components, what we want to be able to do is adjust the seeds that we're crawling. We want to adjust the way our crawler retrieves documents off the internet. In the future, we might want to be able to adjust the PageRank algorithm or adjust other parameters at Seller, but for now, all we're doing is changing our seeds so that we have new stuff to crawl in each iteration of crawling the web. So we start with some static seeds. We go out, we crawl the web, we build our index, we put all of those documents into Seller, then we query Seller to produce a Bayesian network. And then our Markov process generates text from that Bayesian network. The text has source citations. It gives us a weighted list of source documents that contributed to the Markov text that we produce. The theory of operation here is that an individual will look at these results. They'll determine whether or not they're good or bad, or whether or not the seeds that the documents that are being returned to us are useful for the search that we're trying to do. And we'll use that information to generate a new set of seeds and trigger the crawl again. So we anticipate this to be a sort of supervised loop that runs over a period of weeks or longer, so that some researcher or somebody who's trying to do deep search of the web can gradually train the system to retrieve the documents that we're interested in. All right, so that's basically how the system works. And we have a basic search engine. We're trying to retrain it over time. That's it. All right, so let's move on to the more interesting, the things we're going to focus on here more, the Markov and Bayesian bits. All right, so I need to make a a pedantic note here about Markov chains, Markov process, Bayesian networks. I'm going to use this term Bayesian network to refer to the way we are embedding information that we have retrieved from the web. And I'm using this sort of as a shorthand. So because this is a math audience and because some of you may have interest in AI, I think it's important to point out that the model we're using is not strictly a Bayesian network. Bayesian networks are by definition directed acyclic graphs. And to break that down a little bit further, a graph is a set of nodes with edges that point to other nodes. In a directed acyclic graph, all of the nodes have edges that point in one direction. So if you look at the diagram on the left here, all of the nodes on the left have edges that point only to the right. So there's no opportunity for cycles to appear in this graph. Nothing's going to point backwards to make a loop. So that's what we mean by directed acyclic graph. And that is technically what we mean by Bayesian network. Our model does have cycles. Our model more resembles this one on the right, where you might have a node like E, where it can point to itself, or it can point to A, or A can point back to E. We have loops. So this is a directed graph, but it's cyclic. It does not have, it doesn't have the property where arrows only go in one direction. If we want to be really pedantic, we would call our model something like a hidden Markov network. But this is a lot less common in the literature I've read. A Bayesian network is used sort of as a shorthand to describe all of these sorts of neural networks that underlie a lot of these AI systems. Since we're talking pedantically, and since this is a mathy audience who may be interested in AI, I'm going to break this down a little bit further. There are generally two categories of models that are used as a basis for a lot of the AI systems that we see today. The first are finite impulse response, and the second are infinite impulse response. Impulse response means that this is a network of some sort that takes an input and then it runs an algorithm to produce some kind of output. And as you might expect, a finite impulse response network has a finite number of outputs that can be produced from any input, and an infinite impulse response network has an infinite number. Finite impulse response is associated with the true Bayesian networks, things called convolutional neural networks, feed-forward neural networks, perceptrons, things like that. One of the properties here is that all potential responses that this neural network may produce can be unrolled. So we know we have a finite number of responses and we can determine what those responses are without necessarily running the algorithm. In contrast, the infinite impulse response network has cycles. So feedback can exist in this network. It can get into loops. Infinite loops can exist. This is associated with directed cyclic graphs and the hidden Markov model. That's this green box over here. And this is used to implement things like recurrent neural networks, which allow you to move back in the process. One of the key identifying property of the infinite impulse response network is that the potential responses can't be unrolled. You don't know what all of the responses will be because you can have loops and things can be infinite in length. Okay, so the key takeaway here is that gives you a little bit of background into the different types of models and the underlying graph structures that are used to describe them. And the thing to remember is that I'm using this term Bayesian network. It's not technically a Bayesian network because we have cycles. That said, let's move on to our recipe for building a Bayesian network. All right, so this is going to be a little bit convoluted to follow. Let me turn off my video here because it's hiding some of the slide. Wrong video, turn off the webcam. There we go. But I've tried to break the process down into a small number of steps, and we're going to walk through a really simple example. Okay, so our recipe assumes that we're going to take some simple input text here. Our input text, cheese is delicious. I love cheese and fruits. And we're going to assume that we have some sort of math library that can do matrix math or vector math for us to make things simpler. We're not going to walk through the specific math that we're going to do. So I'm going to assume that either you or the math framework that you have in play can do some linear algebra for you. All right, so first off, we need to have some sort of dictionary with words or tokens that can be mapped to unique index IDs. You could pre-build this dictionary with all of the anticipated words that you might find. What our model does, when we take text, we ingest it into the dictionary, and we either, if we encounter something that doesn't already exist in the dictionary, we add a new entry. But that way we are guaranteed to have one unique index for each word that we read into the system. So for our input text, cheese gets the index 0, for instance. Now, because we have a numerical representation of each of our numbers, or at least we have a unique ID, we can move on to step 2, where we vectorize the input. And what I mean by this is that each word that exists in the input string is translated into its index ID, and that number goes into this vectorized input. So you can see that for cheese is delicious, I love cheese and fruit, we get the vector 0, 1, 2, 3, 4, 0, 5, 6. That just corresponds to the IDs in our dictionary, and these elements are in the same order as the input text. The next thing we need to do is we need to imagine that this vector has a set of tuples. There are a lot of ways to break these tuples up. Our model uses what's called a two-gram, meaning that it's a two-tuple. Each tuple represents a current index and then the index that we transition to. So for example, if we are on the token cheese with index 0 and our input, we're reading our input, the next token in that sequence is 1, representing is. So cheese is. So our 2-gram is 0, 1. And then the next 2-gram is 1, 2, representing is delicious. This is convenient when we're setting up a counts matrix because we can take each index, 0 for instance, as a column in this matrix. So column 0 here. And then we can take the second element of the tuple as the row. Say 0 to 1 means that we go 0, column, row, 1. And we increment a counter in that cell. We repeat that for all of our inputs. Our matrix C in this example is pretty simple. It's not super interesting because we only have one instance of each tuple, but it makes it a little bit easier to illustrate. All right, so we've gone through, we've built our dictionary, we've vectorized our input, and then we've counted our transitions in that input. That's step 3. Step 4, we're going to take the sum of each of those counts. Step 4 is going to feed into step 5 pretty directly. So this is pretty easy. We look at each count. So column 0, the count of elements here is 1 plus 1, it's 2. We count up the rest of the columns, and we get a vector. It's the same width as our matrix. It says 2, 1, 1, 1, 1, some number of ones there. I can't count. What's important here is that we're going to use these counts to build a diagonal matrix in step 5. So for each element in our column sum vector, we take 1 divided by that sum, and that gives us an element in the diagonal of matrix D. So for instance, at index 0, we take 1 divided by 2 to get 0.5. We drop that into the first element in the diagonal of the matrix. And we repeat that for all of the 1s. And along the diagonal here, we get 1s. And then in the final element, there's no transition, so there's a 0. Okay, so we've gone through step 5. We have our counts matrix. We have our diagonal matrix. Now what we're interested in is if we are on any given index in our dictionary, index 0 for instance, what are the potential tokens which follow from that specific token? Or what are the potential index IDs that follow from that? So what we're going to do is we're going to build a transition matrix simply by telling NumPy, make all the linear algebra hardness go away, to multiply matrix D by matrix C. And we get matrix M, which shows us transition probabilities. And the way that we want to read this, if we are on token 0, this is going to give us a set of rows here. Each row here with a number represents the probability that our token ID 0 is followed by the token ID on that row number. So for row 0, we have a probability of 0.5 that the next token is 1 or is, or 0.5 that the next token is 5 or and. And that's it. That's our Bayesian network. Okay, so how do we use that? This one's actually pretty easy. So we have this transition matrix. We have a set of columns. All we want to do is pick some token, any token. Let's say index 0 in this example. And then we look at the edges that are connected to that. Remember, these edges are represented by rows in that particular column, column 0. And each of these edges has a probability associated with it. There's a 0.66 probability that the next token is index 3, and 0.165 probability that it's index 1 or index 2. So let's say that we pick, this is a this is a weighted random choice, and it's most likely that we're going to go in this direction. Let's say that's what happened when we made our random choice. So now we just repeat that process. We're on index 3, and we have 2 edges. This one that goes back to index 0, this one that goes back to index 4. We have a 50-50 chance. Let's just say we flipped a coin and we went to index 4. There's nothing to transition to from here, so our Markov chain ends. That's it. All we do is we pick a token, we randomly pick an edge to follow, and we use a weighted algorithm to randomly choose that so that higher weights are more likely to occur. And we record each node that we stop at, and then the resulting string of words is the Markov chain that we've generated. All right, so how do we use that with text citations, for instance? This is one of the things that we were most interested in investigating when we built this project. We wanted to know if AI can generate these Markov chains or generate some sort of output and keep track of the source material so that we have an idea of where the information that we're reading came from. And we took it seems like a relatively naive approach to me, and it is also really memory intensive. I think that our algorithm takes it's more than a gigabyte of RAM to keep citations for 10 or 12 relatively large web pages. So it's pretty big, but there might be better ways to implement this, but the approach that we chose, oops, wrong slide. The approach that we chose is that for each link in our Bayesian network, for each edge in our graph, we want to record which source documents contain that link from that word to the following word, and we want to count how many times that occurs. So if we have token A followed by token C, we can represent that as a tuple. We can say that our transition was index A to index C. And we can take that tuple and use that as a key in a Python dictionary. So for any source document that has that specific transition, we will add that source document to our dictionary of sources, or we will increment the count for it. And this is what it looks like in Python. This is a really simplified example. On the left here is a more graphical representation of what the graph data structure looks like. So when we produce our Markov chains, instead of just grabbing the words that we stop at in each node, we also grab the source dictionaries so that we know which sources contributed to that Markov output. And that's pretty neat, I think. Okay, lastly, we produce some Markov text. We produce Markov chains that have some statistical representation, or they are some statistical representation of the documents that we ingested. We, as users of this system, want to search for specific strings, or we want to know how similar the Markov chains that we produce are to some target text. The simple way to think of this is search. We're searching for some string, and we want to find things that are similar to our string. A more complex way to think of this is that we have text that is produced by our system, and we have static text that we want to compare the produced text to. and we want to select produced text which is most similar to our target. And I'll show you an example of that a little bit later on. But here's how cosine similarity works. First, we take two input texts. In our case, the input text will be a Markov chain that we produced from the Bayesian network, and it will be the target text that we're trying to match against. Next, we make a list of all of the tokens that exist in either text. We only care about the unique tokens. Now, for each input text, we make a count of how many of each unique token exist. So for each unique token in our list, that represents the index ID in our two resulting vectors. We just count up how many words of that type exist in either text. This produces two vectors. These vectors have n dimensions in some n-dimensional space, where n is the number of unique tokens that exist between both of these documents. This is a lot easier to visualize if your documents only have 3 unique tokens, but computers don't need to visualize 4D in higher space, so we just need to do some math. In this case, the math that we're doing is to apply the Euclidean dot product formula to find the cosine that exists between these two multidimensional vectors. So we choose cosine here because it gives us a convenient scalar between 0 and 1. That scalar can be used as a score that tells us how similar these two texts are. Higher scores mean that the texts are more similar. Lower scores mean that the texts are not so similar. So I use NumPy here and some math libraries to do all the summation and the square roots. And the text is actually, the source code is actually surprisingly easy for that. All right, so we talked about a lot of things there. We're building a Bayesian network. We are generating Markov chains. We have some auxiliary source citation mechanism when we generate these chains. And then we have a way to judge the quality of the chains as they compare to our target text. So we'll review that a little bit. I'll talk about the pipeline that we're following when we're processing text. I've skipped over the part where we clean the text as it's being ingested. It's not super interesting for this presentation, but essentially we take regular expressions and we remove certain patterns, things like text citations, or URL citations in Wikipedia pages. Next, we tokenize into the n-gram model. We build the Bayesian network. Once we have the Bayesian network in place, we generate a Markov chain by doing this weighted random walk over the Bayesian network and collecting the tokens at each node that we stop at. And again, this is also where we're collecting our source citations. And then cosine similarity is where we generate a Markov chain and we compare it to a target text and we give it a score. Let's see, forgot that the webcam's not on. I'm gesturing to you all and you can't see my hands. Cosine similarity allows us to generate a Markov chain and compare it to some target text. What our model does is we have some maximum number of tries that we'll apply. It defaults to something like 100 tries. And we have some target score. Our default is, I think, 0.7. Maybe it's a little lower because I've got it tuned so that it responds quickly. But it just runs until it either finds a match that is at or above our target score or until it runs out of tries. And then it returns that to the user. Okay. Yeah, I guess a quick review on the text pipeline would be good. Text cleaning, we clean up the text so that it's easier to read and we have less garbage in there that's not interesting to us. We build a Bayesian network, we generate Markov chains, and then we have some way to generate text and compare it to a target, in this case, cosine similarity. All right, let's look at some demos. First off, these are just some screenshots. I want to call your attention to these QR codes here on the bottom left. Again, I can send you these slides later. I can send you either of these links if you're interested. Top QR code points to our website where we have an Ionic app running. And the bottom QR code points to our GitHub repository where all of this Python code and sorted other stuff to make this work is existing. We're going to ignore these two on the left because I'm going to show you a live demo. Yeah, I'll show you a live demo for as much of this as possible. I'm not sure if we'll get to the Ionic app, but this is what the website looks like in the bottom center here. Top right here. So early on, we built a sort of toy Markov bot. It didn't have weights. It wasn't using any of this matrix math. It just used Python dictionaries to build some graph structures. And we trained it on some poetry and allowed it to learn phrases from a Discord chat. It was just sort of a quick demo of a Markov bot that can talk to people in Discord. And we were all pretty amused when our bot said, "Oh, what can ail thee, knight at arms? Peanut butter bacon time at Sonic." I was amused. Okay, so let me switch over to our Discord channel where the bot is running. And hopefully my keyboard is not too loud, but I'm going to show you a quick demo here. Okay, so first off, let's do a search. We're using Discord / commands here. We'll do loom search, and our two required parameters are a match target. Let's search for something like coconut cream pie. Why not? Let's say we do want it to show our sources, so this is going to give us a weighted list of the source documents that contributed to our Markov chain. We have two optional parameters here, max rounds and target score. We talked about the cosine similarity algorithm. So we have a maximum number of tries that will try to match some target. Let's set it really low for now. We'll try 25 rounds. And we have some target score. This is that number between 0 and 1, which represents the cosine between those two angles. And let's set that pretty small too, to 0.5. And we'll hit enter. This is going to run. It's sitting out there thinking. Okay, so, oh wow, we got a pretty good target match score there pretty easily. One thing you'll notice about this text is that it's not super legible. And this is one of the features, or it's one of the challenges with Bayesian networks and producing text in this manner. A lot of the more advanced AI techniques try to train models that produce text that's more legible. Ours doesn't do any of that because it's a lot more complex and it's not super interesting for just trying to learn the rudiments of how these systems work. But we've produced some text, which is in theory somewhat associated with coconut cream pie, given the text documents that we ingested into the Bayesian network. Doesn't seem to have a lot to do with pi to me. Large masses, alpha decay, adjacent pictures, according to deflect the high mass of Sir Isaac Newton, and magnetism. Well, maybe pi has something to do with the large mass of Sir Isaac Newton. So there's a lot more that we can do to make that text legible, but it gets to be really complex really fast, so we skipped it for this project. What's interesting here, however, is that we have this weighted list of the 3 source documents that most heavily contributed to the Markov text that we've produced. So if we were to click through, we would see a lot of 2-word links in these alpha ray and atomic nuclei articles on Wikipedia, maybe a few less for this atomic theory article on Wikipedia. Okay, so if you recall the system slides that I showed you earlier, one of our goals is to run a fresh crawl on the web with new seeds and then adjust the search parameters that we use for our bot. So let's take a look at, we're not going to do a fresh crawl because, as I mentioned, that can take hours or days or weeks or longer, but we're going to assume that there are some documents that exist in our index and we might be able to adjust how we're training the Bayesian network and how we're querying the Bayesian network to get better results. So we're going to skip the start crawl option here. We're going to skip check crawl. Let's try change query. So actually, first I'll show you show query. What was it? Show. Here it is, print query. So this is the query that's currently running against our Solar instance. We could click on this. Actually, let's do that. Hopefully this doesn't blow up on me. Copy the text. Let's open a web page. And currently our query is set to search for pudding. That's cool. But this is a real response from our Solar instance. And let's take a look at that. Why not? This is Solar. This is the administrative page for Solar. There's also a query page here. Let's see if this will work. No. Okay. I don't remember specifically how to query the UI, but that's not important right now. What we want to do is we want to change this query so that we're not searching our index, our Solar index, for pudding. Let's say something like we want to change our query to, what do we want to build? Let's search for American football. That usually yields some interesting results. Okay. So that has updated the query that will run to build our Bayesian network. I'm going to start that process. Let's say we're going to reload docs, which means we're going to query Solar and build a new Bayesian network. So that's running. It's going to take a moment. Let's see if I can show you what's happening on the back end. Okay. Looks like it's maybe crashing. Oh, that's fun. Let's see if we can fix this real quick. Yeah, it looks like it got stopped. Okay, so let's just restart our bot. Okay, so I've restarted the bot, and it's doing the same thing where it goes out and it runs the query. So when we queried Solar, we found these documents. American football, for some reason, returned a lot of documents related to helium. This is going to be related to how we crawled the web in the first place. Our seeds had a fairly heavy bias towards Wikipedia articles, and specifically the 118 elements of the periodic table. So let's see what we can learn about American football as it relates to helium. Okay, let's turn off tmux and look at Discord again. And we might need to refresh this. Yeah, that's just going to sit there spinning. Okay. We're just going to do a new query for, let's search for, gridiron football and see what sources we have. It's thinking. Okay, so it's running the cosine similarity process here. We've done 25 and 50 iterations. I think 50 is our default stopping point. Yes. So it produced something that matches cosine of 0.64. And again, we're not seeing a lot associated with football, but that shouldn't be surprising because we crawled for things related to helium and for the periodic table. Let's search for helium just to see what happens. And we'll show our sources. And I'm watching 25, 50 iterations. Okay. That seems pretty similar to helium. So when we're searching a Bayesian network, that's interesting that the score is so low, though. I don't know. So there are a lot of things that we can conclude from this, a lot of things that are kind of interesting to observe as we play with it. Mostly what we found is that we can, actually, let me show you my conclusion slide. We'll talk about that. Let's turn off Discord and look at the slide. Okay. So we have learned that it is possible to train a Bayesian network on web content. We shouldn't be surprised by this. This is what generative models like ChatGPT have been doing for some number of years. We've learned that we can generate text with citations. This wasn't very surprising either, but I haven't seen other chatbots doing this before, so I'm pretty excited about that. Um, we have learned that our text citation model is really memory intensive, so there may be some optimizations that can be made in how we're managing that, but ultimately the model that we're using favors topic-specific small data search. So ideally, the memory limitations aren't as severe for us as they might be for a large pre-trained model like ChatGPT. We've learned that we can adjust crawlers and retrain a search engine dynamically. So what we set out to prove essentially, or the prototype that we set out to build was, can we build a small topic-specific search engine that uses AI tools to help sort of summarize the content that we're searching for? We were able to do that. Of course, as you're seeing from the demo and the example that I'm showing you, making this useful for any sort of real-world web search is going to require a lot more work. There are a lot of more advanced AI techniques that we would want to bring to bear. It's things like transformers, stuff like that, that allow us to summarize and categorize data as it's produced by this model. A lot of pre-training that we might want to do to make things more readable and more usable for an end user. But as a proof of concept, we think this works really well. We need to be careful to mention, though, that it is at best a proof of concept of this idea. And again, I talked about this a little bit, the limitations of the model. We're never going to be fast like a pre-trained generative AI because this isn't really pre-trained. We're doing dynamic training on demand. A lot of the advantages that models like ChatGPT have is that in addition to using more advanced tools and techniques for AI, they're going through a lot of iterations to train what they call embeddings. Embeddings are basically just the way they store the network that has been trained, and then they're querying against the embedding in real time to produce results for end users. Our system isn't doing that so much. We're doing a lot of dynamic retraining and training on demand. But one of our advantages here is that being retrainable means that we can adapt to user needs. And that was always the goal. We want to do small scale search for topic specific things, and we want to be able to adapt our system to the needs of the user. So we think that this may provide a niche for web search. This topic specific deep search concept, it might be useful for researchers, or it might be useful for individuals who have specific interests who are trying to work around ad supported search. Anything that you're trying to discover on the web or on the internet that isn't necessarily served by the middle of the bell curve, which is what Google is going to try to give to you. Now, ultimately, what we've gotten out of this is a lot of learning about how systems like this work, a fair amount of learning about how the fundamentals of AI systems work, but most of all, it's given us a lot of ideas about what we might do in the future. So we want to use this. If we stick with this project, I think I might. I don't know what my teammates are going to do. But if we continue working with this, we want to use this as a foundation for improved tools to manage the search engine backend. We want to use more advanced AI concepts, things like transformers or Mamba, which will produce more readable results. It'll help us categorize documents and things like that. RAG is retrieval augmented generation. I should have something on here about generative adversarial networks. So a GAN. GANs are basically two Bayesian networks that are producing Markov chains in competition with each other and randomly adjusting some of the weights. And then they use some sort of mechanism to compare the quality of the texts that are produced, something like our cosine comparator. And whichever one mutates the inputs the best to produce the best outcome is the one that wins and evolves and improves over time. That's what a generative adversarial network is like. All right, so that is Loombreaker. Ask me sometime offline why I've called it Loombreaker. It's a little interesting, but it's also kind of dumb. But if you have any questions, feel free to reach out to me on email. I'm going to stick around in this Zoom chat here. Feel free to look at this code on GitHub, play with the website. We can give you invites to a Discord channel, whatever it is you're interested in. Just reach out to me and I can help you out.